Thank you. We're going to talk about how to tell what people are watching, and this is important because video traffic is interesting. It's interesting for targeted marketing purposes, and it's interesting for market characterization efforts, and we've seen such efforts commercially in the past. And so luckily, because not everybody wants to volunteer this information about their habits, video traffic is also encrypted. And so HTTPS has been in wide deployment in these, in at least the major streaming services. And as of last year in Netflix, as of this year even in Pornhub. And so we ask, what can we still learn about how effective are these measures, or what can an attacker still learn even though there is HTTPS encryption? And so to answer that, we consider the scenario of a traffic analysis attack where a streaming service is transmitting information over an encrypted channel to a victim, and there is an attacker who may not be able to observe the packets that are going on the wire or the packets of the video itself, but he can observe maybe some metadata, for example, packet times and sizes. And if he can observe this metadata, then perhaps he can also tell what the victim is watching. And if he can, then that means that our encryption is far less efficient than we thought it was. And for the specific case of a streaming session, what an attacker would observe if he's only observing packet times and sizes is he would see an initial period of buffering where the client is receiving a lot of packets, followed by a steady state where packets come in bursts. And every few seconds we have a burst of packets. And this behavior has been observed by traffic characterization researchers, but they did not specify where do these bursts come from, why do they happen. So we're going to take a look at that. And to answer that question, we're going to take a look at how videos are being represented, how they're being stored on the video server. And obviously, video server contains a bunch of these videos. And there is a standard called MPEG-DASH that is widely adopted by Netflix, YouTube, and well, at least it's the behavior of it that is relevant to us is adopted by Netflix, YouTube, and all other major streaming providers. And if you adopt this behavior, then typically what you would the way you would represent a video on your server is you would have a bunch of segment files, where each segment file stores a few seconds of content or a segment. And the reason for that is that the client-server interaction that the MPEG-DASH standard prescribes is that the client basically does a loop over this condition. Is my buffer below a certain threshold? And once the buffer crosses some threshold, it goes on and fetches a segment. Now, when it fetches a segment, then it has a few more seconds of content. And then after a few seconds, the buffer crosses this threshold again. So every few seconds, we'll have segment fetching. And segment fetching, segments are a few megabytes big or a few hundred kilobytes. So segment fetching causes a traffic burst. And so that's where the bursts are coming from. Now, another thing that has been noted about videos specifically is that videos are a lot of the times variably bitrate encoded. And this means that it takes a different amount of bytes to encode different seconds in the same video. And this is well illustrated by the iguana versus snakes video, which is a video of an iguana being chased by snakes. And we'll also see that there is a certain correspondence between the content of the video and the variable bitrate pattern. So the variable bitrate pattern is below the video here, and we're actually going to watch the video. So in the beginning, we have a lot of movement, and the bitrate is a little erratic, but mostly high.
A snake's eyes aren't very good, but they can detect movement. So if the hatchling keeps its nerve, it may just avoid detection.
And then there begins a scene where, or the tension is arriving some sort of peak, and we see a headshot of the iguana, a headshot of the snake, and then a very still scene of the snake creeping up behind the iguana. And this, since it's very still, it takes very few bytes to encode this. And then there's the chase scene. You can see how the bitrate climbs. And then the iguana is almost captured. And again, we have a still image of the iguana trying to escape the snake, and you see how the bitrate drops for a few seconds. And then it breaks free, and the bitrate climbs again. The iguana is climbing some rocks. The cathartic ending where the iguana is safe and is again still, and it also has the BBC logo, and it apparently takes very few bytes to encode that. So we see that there is a correspondence between the content and the variable bitrate pattern. And if there is variable bitrate, then that means that segments are also, each segment is of variable size, is of a different size, because segments are of a constant duration. And if segments are of different sizes, then bursts are of different sizes as well, because bursts are just segments being downloaded, and we can see that in the traffic very well. So there is a leak here that goes all the way from the content of the video onto the burst size patterns, which is that the content of the video leaks onto the variable bitrate pattern, or at least characteristics of it leak, and the variable bitrate pattern leaks partially onto the segment sizes. The segment sizes correspond directly with burst sizes. Now, so we have a pattern that is dependent on the content that is observable on for the attacker. But can this pattern be used to identify a title? And this question breaks down into two different questions. First, does this pattern uniquely characterize a title? And the answer to that is that empirically, at least for the 3,500 videos we downloaded from YouTube, then 20% of them have a uniquely identifying pattern. And the second question is, can we learn this pattern and use it to identify the video? And that translates into is this pattern consistent? And the answer is, of course, it's consistent, because bursts are just segments, and the way that segments are stored on the server does not change. So the pattern is consistent. So we conclude that 20% of the YouTube titles have fingerprints. But the fact that they have fingerprints is nice, but we want to show an actual attack. So, and the attack goes like this. First, the attacker streams videos, performs streaming sessions into its own network, and he collects metadata about these streaming sessions. And this metadata is used to train detectors, which hopefully for the attacker, given the metadata of a specific streaming session from a victim network, are able to identify, yes, this is one of the videos on whose metadata we trained, or no, I don't know this video. And two things I need to specify about this scenario. So first, this is the vantage point. So I didn't explicitly say it, but I didn't explicitly define the attacker. So now we're going to define the first attacker. So the first attacker is an attacker who can observe at least packet directionality and sizes and times. So it's a pretty powerful attacker, and it's an attacker that's limited to a set of pretty powerful entities, such as your ISP or a national network sensor or whatever. And I'm going to relax that requirement later, so I'm going to expand the adversarial model to weaker attackers. But this is the first one, so let's consider this for starters. And the second thing I need to specify about the attack is the machine learning approach that we're taking, which is going to be, we're going to use deep neural networks. And we know that deep neural networks are very good at learning some high-level concepts that humans can easily agree on, but find it hard to formally express. But for us, for our purposes, they are good. They are better than other approaches for several reasons. First, that they can operate on relatively noisy data, which is, we'll see how that comes into play later. Second, they are agnostic to protocol-specific attributes. So if YouTube uses QUIC and Netflix uses TLS, we don't have to fit anything in the attack for a specific streaming service or for a specific protocol stack. Third, they can learn features that are not just burst patterns. So if other characteristics of traffic can be used to identify a title, other than the burst pattern that we are talking about, then these classifiers hopefully will pick up on them, and that's a good property. We want to take advantage of that property. And fourth, we don't have to worry too much about representation. We can use multiple representations, and the network will learn the better one. So that's what we do, and we represent the title using a bunch of a few vectors, and each vector is a time series sampled at 0.25 second granularity of the downstream, upstream, and total packet size series, and we represent the title by using a bunch of vectors, and we input that into the classifier. So now I've specified the attack, and let's now specify the data sets that we're using to evaluate this attack. So first, Netflix, we collected 100 titles and 100 one-minute sessions per title. This defines a classification problem of 100 classes. And for YouTube, we did a very similar thing, except we have 18 classes, but then we also added another class that contains 3,500 sessions of different titles. And this is more similar to a detection problem than a classification problem, because our YouTube classifier differentiates between sessions of titles that it's never seen before and sessions of the 18 titles that it is trained to identify. And we also did similar things for Amazon and Vimeo. And we have accuracy results that are good across all these data sets. And specifically for Netflix and YouTube, they're about 99%. For YouTube, we also have exactly 2 false positives in our data set for our classifier. For Netflix, we have no recurrent confusion, so there are no 2 titles in the 100 titles we collected from Netflix whose traffic traces are recurringly similar. And these classifiers, they output a confidence measure in their prediction, and we use that to tune them for precision over recall. And we attain 0 false positives for YouTube and 0.0005 false positives for Netflix. And now I want to take a step back, and I said I would discuss another adversarial model. So now I'm going to do that. So let's assume for a second that we're not a powerful ISP or a network moderator, and we don't have access to very fine-grained access to actual packets and their sizes that are being transmitted from the streaming service to the victim device. But we're just an adversary who has only a limited foothold on the victim network. For example, we are a visited web page or a smartphone application. And specifically, let's consider the scenario where a user is checking her Facebook feed while she's streaming content into a smart TV. So she's streaming Armageddon, and she's also accessing her smartphone and opening her Facebook feed. And to the right of her Facebook feed, there appears a web ad. And this web ad is malicious, and it really, really wants to know what the user is streaming right now, so it can present content that is targeted for this specific moment where she's streaming Armageddon. And this web ad would have to deal with a very strong notion of confinement, which is that it's on an entirely different device. It's inside an isolated browser process, which has less capabilities than other processes. And it's running JavaScript code, which has very little capacity to learn about its surroundings. It is sandboxed by the browser sandbox. But what they do share, these two devices, the smartphone and the TV, they do share a network link. And that is the link between the home router and the internet. And it is also a bandwidth limited link, and we're going to take advantage of that. So consider the following attack. We have a viewer device and the neighbor device. They map to the viewer and smartphone in the previous slide. The neighbor device is accessing some attacker website. The attacker website sends its malicious client code, and it starts sending messages to this client code. And all that the client code is doing is timing the arrivals of messages from the attacker website. And the messages are big enough and they're frequent enough to create congestion on the link between the home router and the internet. And when there is congestion on this link, then as bursts come into the viewer, the attacker client will experience delays. And hopefully for the attacker, these delays are some sort of estimate of the burst sizes that are going into the viewer. And we evaluated this scenario, and indeed, from the point of view of the attacker, it looks pretty good. It looks like we have, on this slide, we have traffic burst sizes in red, and their times. And for every traffic burst size, we see a surge in the message delays that the client is observing. And if we take this, this surge and we sum it to have the aggregate amount of delay induced by every traffic burst, then we get a time series that is very, very correlated, that is correlated very highly with the time series of actual traffic bursts. And since it's correlated so well, then we can expect it to uniquely identify the video. And indeed, as we tested our classifiers on just this feature, we got very high accuracy, almost comparable with what we had when we were observing it on the wire, albeit with slightly longer recordings. And it can be noted that this is a cross-device scenario, but trivially, this is also a cross-site attack because the viewer and neighbor can just reside on the same device. If one browser tab is streaming something, the other browser tab is accessing some malicious website. That's a cross-site attack. And now I want to conclude with talking about mitigations. So this attack stems in two facts. The first is that if you take the first few seconds of a video and you take the next few seconds of a video and the next few seconds and you measure how many bytes it takes to encode each of these segments, then you get a pattern that uniquely identifies a video. And the second fact is that fetching is done at the granularity of a few seconds. So this is exactly the pattern that an adversary who cannot observe content but only metadata, this is exactly the pattern that he can see. And so mitigating this leak means tackling and changing one of these facts. And changing variable bitrate to constant bitrate seems like it would be way too expensive because we want variable bitrate. It's a good thing. It allocates bytes where bytes need to be allocated for rapidly moving scenes and not to still images. And fetching at this few seconds granularity means playing around with a bunch of factors in streaming that we might not want to be playing around with. For example, we can increase segment size by a lot, but that would mean that streaming becomes less adaptive to changing network conditions. We can randomize stream segment sizes, but that would mean that the user might experience delays in the playback because maybe he will get a series of too small bursts, too small segments. And we can we can increase the buffer size to make the streaming more robust to that, but then we end up with something that's more like download and less like streaming. And the point is that these things are optimized to maximize some measures of efficient streaming that we know about. And it seems like changing them to promote privacy would mean hindering one of these measures, and we don't see the industry going there right now. But listen to the next talk, and maybe we'll have some insight from that. That's us.
Thank you. So are there any questions? So we have 2 microphones here. If you come up, please state your name and affiliation.
Hi, great talk. Have you considered the fact that a user may be also torrenting during downloading the video, and also on Facebook, and also, adding noise to the home network router?
Yeah, so other types of traffic that are not streaming, if the user is streaming 2 videos at one time, it would probably be detrimental to classification accuracy. But if he's using, we did not evaluate the scenario, but if he's using other things other than if he's just going on Facebook, then it would induce some level of noise, but our classifiers are expected to behave well in that scenario, since they are, we do show that they are robust to some noise.
So a lot of this problem happens because of the variable bitrate encoding. It's because the sizes are different depending on what you're seeing. So one fix would be to move to fixed bitrate encoding. And so what's the overhead on that with respect to like the realistic movies that people watch? That's question 1.
It would be hard for me to quantify that.
Is it like twice as much, 10 times as much, 1.01 as much?
That really depends on the video. The more variable bitrate encoded it is, the more overhead it would incur. We can see that Netflix videos are very variable bitrate encoded. Their bitrate varies significantly. I don't have the number, but I can take it offline.
Okay. Yeah, and I guess the follow-up is there anything in between that was not fully fixed,
yes,
but protects you better against this attack? And I'm curious.
Yeah, the answer to that is yes. I mean, it's you can play around with the encoding parameters so that to have bitrate that has some constraints on its variability. You can do that.
August Rees, Google. So early on in the talk, you said that only about 20% of videos had unique fingerprints. For the other 80%, are they all mutually indistinguishable from one another, or are there like clusters of identification where you can distinguish the clusters but not the individual videos within?
There are clusters, yes.
Thank you.
Specifically, if the videos are constant bitrate encoded, then obviously there are clusters because it's just bursts of the same size, and when they are encoded in the same bitrate, then that will be a cluster. But even in videos whose bitrate varies, we've observed clusters of them, yes.
Thank you.
So it seems like a simple fix would be, instead of chopping the video by fixed number of seconds, you do it by the fixed chunk size, so that it becomes variable number of seconds.
Right, and that would mean that the leak goes on to the number of seconds. Yeah, it's something that always comes up. Yeah, it's the leak would just be the amount of time between 2 segments.
All right, thanks.
Are there any other questions? So I've actually one myself.
Yes.
So the when you do the cross device attack, so how much traffic do you need to cause with the monitoring process? Is that something that is noticeable that it's running in the background on the phone or something?
We don't in our evaluated in our experiments we did not fully saturate the link, but we nearly saturated it, and because of the router's discipline of not starving any flow, even if we did fully saturate it, it wouldn't be noticeable in terms of the streaming, unless the streaming itself takes more than half of the bandwidth. That depends on the configuration, but under reasonable configuration, if the streaming itself takes more than half of the bandwidth, then maybe we will see some degradation. but that usually does not happen.
So it's not very obtuse.
Yes, and we did not observe any. It's indistinguishable as far as we could see. Yeah.
All right. Thanks, Roei, again.